We have been discussing about the implications of Mach number in the previous lecture. We will continue that with some numerical examples. So, first we will work out a problem which is a very simple problem, does not even involve the Mach number, but we will start with that. A weak pressure wave, which is essentially a sound wave with a pressure change of 40 Pascal, propagates through still air at 20 degrees centigrade and 1 atmosphere. Estimate the density change and the velocity change. So, what is given is dP as 40 Pascal. Ideally we should write this as delta P, right. This is not differentially small, but in a casual way I am writing this. So, if you feel that we should write it in a more formal way, this is delta P. P is equal to 20 degrees centigrade and P is equal to 1 atmosphere. Okay. So, now the velocity change is related to pressure change through the momentum equation that we derived in our first lecture on compressible flow. So, I will just write that formula for you. So, dP or delta P is equal to rho C delta U. Okay. So, you can get rho from the equation of state, P by rho equal to RT. You can get C as root over gamma RT and delta P is given, which is 40 Pascal. So, from this equation you can find out what is delta U. So, delta U answer is 0.097 meter per second. And how do you get delta rho? Delta rho you get from mass conservation. So, mass conservation, so this is momentum conservation. Mass conservation says that delta rho is equal to rho by C into delta U. This we have all derived, this is nothing new, we have all derived. So, once you know delta U, you know rho and you know C, you can find out what is delta rho. So, this delta rho is 0.00034 kg per meter cube. Okay. So, this is a simple enough problem that essentially requires the skill of using the mass and the momentum balance that is required to analyze the movement of the pressure wave. Next problem. A supersonic aircraft flies horizontally at 1500 meter altitude with a constant altitude, sorry, with a constant speed of 750 meter per second. The aircraft passes directly over a stationary ground observer. How much time elapses after it has passed over the observer before the observer hears the aircraft. Assume sonic speed is 335 meter per second and the aircraft creates a small disturbance that may be treated as a sound wave. So, let us see what is given. So, there is a man or a woman, there is some observer who is standing here. I mean the aircraft is at such a height that this is like almost on the ground, and this person is at 1500, h is equal to 1500 meter down the aircraft is moving like this. Aircraft is moving with a supersonic speed, that means all the locations do not understand the disturbance, only when you enter into the Mach cone then only you enter the disturbance, then only you understand the disturbance. So, this observer is here, aircraft, let us say when the aircraft enters here, at that location the Mach cone just passes through this, and then this observer understands that there is a disturbance. Let us say this is the Mach cone. So, the speed is given which is u is 750 meter per second. You have to find out what is this time delta t at which this Mach cone just passes through this, and this angle is the half angle of the Mach cone or semi vertical angle. So, tan theta, sin theta. So, we have the formula for sin theta, right, sin theta is equal to 1 by m, right. So, now you can write what is m, u by c, u is 750 and c is 335, right. So, you will get theta from here. Now, from the geometry of this figure, you have tan theta is equal to h by u delta t. You know h, you know u, you know tan theta. So, from here you will get what is delta t. So, delta t is 4.006 second. Okay. So, we have worked out a couple of problems. The next concept that we will learn is a very important one, that is called as stagnation properties. Stagnation is an English word which essentially means bringing to rest or a state of standstill, so to say. So, if you have a flow where say you have a fluid flowing and you assume a control volume like this with properties uniform over the sections 1 and 2, we will try to see that what will be the property at section 2 if the fluid is brought to rest in an adiabatic process. Okay. So, essentially if the fluid is brought to rest in an adiabatic process, what is that corresponding property that we are interested in. So, you can write the first law of thermodynamics for the flow process. So, what is the first law of thermodynamics? Q dot, that is the rate of heat transfer, we will of course write U1 square by 2 plus GZ1, but we will neglect the GZ1 part. So, this is enthalpy. So, remember that when we were earlier writing the first law of thermodynamics, it was not for a flow process, it was for a control mass system, closed system process. So, there it was internal energy. For a flow process, you have the energy, thermal energy as internal energy plus flow energy. So, that together is called as enthalpy. So, enthalpy, kinetic energy, potential energy. Now, we will make certain simplification. This is the general first law of thermodynamics that we have written. So, we will neglect any work done, this is very important, and this is an adiabatic process. So, the fluid is considered to be adiabatically changing its state from 1 to 2. At 1 all properties are uniform, at 2 all properties are uniform. We also neglect changes in potential energy. So, H1 plus U1 square by 2 is equal to H2 plus U2 square by 2. Now, we consider a special case when U2 is equal to U0, that is 0. This 0 is called as stagnation state, that means the fluid has come to a stagnation or a stagnant condition here. Remember, this stagnation property is a reference property. So, with respect to that reference property we can calculate other properties, and that is why the stagnation property is so important. So, if U2 is 0, H2 is H0. So, you can see that this reference property we can write in terms of the enthalpy and the kinetic energy. So, we can write in general H naught is equal to H plus U square by 2. We have dropped any subscript because this H refers to that state at which we are calculating the property. Now, for an ideal gas, dH is equal to Cp dt. So, accordingly if you integrate this from state H to state H0, so H0 minus H is equal to Cp into T0 minus T. What is the assumption? Assumption is that it is a calorically perfect gas. There is a difference between ideal gas and calorically perfect gas. Ideal gas will have in general Cp and Cv variable as a function of temperature. A special case of an ideal gas is Cp and Cv are constants, that is called as perfect gas or calorically perfect gas. So, this is the assumption is calorically perfect gas. So, Cp into T0 minus T is equal to U square by 2, right. So, U square is nothing but m square C square, that is the definition of Mach number, and C is square root of gamma RT. Remember, this is the definition of Cs, but that we commonly use because most of the flows can be treated as isentropic flows. So, m square gamma RT by 2. So, T0 is equal to T into 1 plus gamma R m square by 2 Cp, right. Now, we can express Cp in terms of gamma and R. So, gamma is Cp by Cv and Cp minus Cv is equal to R. So, Cp minus Cv as Cp by gamma is equal to R. So, Cp into gamma minus 1 by gamma is equal to R. So, gamma by Cp is equal to gamma minus 1 by R. So, T0 is equal to T into 1 plus gamma R by Cp is gamma minus 1 by 2 m square. So, that means you have T0 by T okay. So, similar to T0 by T, we have expressions for P0 by P and rho 0 by rho. So, let us try to calculate that or find an expression for P0 by P. So, now you have P by rho to the power gamma is equal to constant. So, first let us find out what is P0 by P. Now, you have PV right. So, if you combine these two and eliminate rho, what you will get is okay. So, what you do is simply you eliminate rho. Okay. So, if you eliminate rho, you will get a relationship between T and P, which is this one. So, P0 by P is 1 plus gamma minus 1 by 2 m square to the power gamma by gamma minus 1. This is P 0 by P. And you also have P 0 by rho 0 to the power gamma is equal to P by rho to the power gamma, because P by rho to the power gamma is constant. That means you can write rho 0 by rho is equal to P 0 by P. So, rho 0 by rho is P 0 by P to the power 1 by gamma. So, this is 1 plus gamma minus 1 by 2 m square So, the moral of the story is that given the Mach number and given the pressure, temperature, density etc., we can find out the stagnation properties as the reference properties, and if the flow is isentropic, what does not change is the stagnation property. So, that means the stagnation pressure, the stagnation temperature, all these things they are expressed by this relationship, right. So, for a given reference state the stagnation property is unique for a given Mach number. Okay. Now, it is very interesting to see how this relates to a incompressible flow limit. So, let us consider an incompressible flow limit and find out the stagnation pressure. Stagnation pressure in an incompressible flow limit. So, for an incompressible flow you can use the Bernoulli's equation. So, Bernoulli's equation, you can say that why just incompressible flow, you also require inviscid flow. So, when we are talking about the stagnation property, we are assuming that it is an adiabatic process and we are also considering that it is a reversible process for this case. So, the fluid is brought to rest in a reversible and adiabatic process. If it is irreversible, there will be friction or viscous dissipation and you can no more use the Bernoulli's equation. So, the Bernoulli's equation if we write P plus half rho u square is equal to P 0 plus half rho u 0 square, the assumption is that we are assuming that it is reversible and adiabatic. So, a very important subtle difference, when we are talking about stagnation temperature we are perceiving that the fluid is brought to rest in an adiabatic process. Reversibility we are not bringing into the picture, second law we are not bringing into the picture. When we are considering stagnation pressure in an incompressible limit, we are considering the flow to be brought to rest in a reversible and adiabatic process, because if it is not reversible then there will be friction and Bernoulli's equation will no more be applicable. So, P 0 is equal to P plus half rho u square is m square c square, right. C square is gamma RT. Right, this Cs we are assuming, and we know from ideal gas that P by rho is equal to RT. So, rho RT is P. So, that means you have P0 by P is equal to 1 plus gamma by 2 into m square. This is incompressible flow limit, and this is compressible flow limit. So, how can you get the result of the incompressible flow limit from the compressible flow limit? Let us make a binomial expansion of this. So, from this P0 by P, so it is 1 plus x to the power n. So, that is equal to 1 plus nx plus higher order terms, right. So, this will get cancelled. So, this will be 1 plus gamma by 2 m square plus. So, higher order terms will be of the order of the higher powers of m square. So, if m itself is small, its higher powers will be smaller and smaller. So, then higher order terms will be neglected and you will come up with the expression for the incompressible flow limit. But still the subtle difference in the way in which this is derived has to be carefully understood, that this is derived by considering reversible and adiabatic process. So, the stagnation pressure is defined as the pressure at which the fluid is brought to rest in a reversible adiabatic process, whereas the stagnation temperature is defined as the temperature which is attained when the fluid is brought to rest in an adiabatic process. This definition of stagnation pressure is an indirect definition where the relationship between pressure and temperature for an ideal gas is used, whereas this is an explicit relationship of stagnation pressure. So, today we have learned what are the stagnation properties, how these properties are defined, and very interestingly we have found out that these properties are unique functions of the local pressure, volume, pressure, density, temperature and the Mach number. So, that gives us a clue about using the stagnation properties as reference properties for calculations in compressible flows. The situation however becomes significantly more interesting when m itself starts varying, and that happens when the flow occurs through a variable area passage instead of a constant area passage. We will take this up in the next lecture. Thank you very much.